So let's get started. So today we'll look into what is called direct numerical simulation. So this is one of the technique what we call, let's say, an Eddy resolved technique. Eddy resolved method. So there is resolve means capturing or computing, right? Capture. So you are going to capture these turbulent vortices and eddies. So you may question, what were we doing so far in the RANs, right? You were modeling them. So in RANs you modeled all the eddies except the largest one, right? Entire spectrum. So this is opposite to that, where we are going to capture, and there are many methods. So this is one of the method, okay? DNS is one of the Eddy resolved method, and here another point to remember is that we don't use any turbulence models here, okay? No usage of any turbulence models. So then the question comes, then why are we studying this, right? This is a turbulence modeling course, then why are we studying a technique which does not use turbulence models, right? So we will look into this, why this is useful. And we have been looking into, while modeling, we take help from DNS data to actually model. So the data here is coming from first principles, from Navier-Stokes equations, where we are not modeling turbulence at all. We are entirely relying on Navier-Stokes to tell us what this flow looks like. So from that we can, once that flow is computed, you can of course apply your averaging techniques. You can decompose the flow, look into its budget, how much turbulence is produced and who is producing it and who is dissipating it and all these things, and that information you can use to improve your model, produce new models. So the data is useful, right? It as good as experimental data, sometimes even better than experimental data, okay? So we will see like how you can do this, how you can do a direct numerical simulation, and what are the parameters that are required to call it a direct numerical simulation, okay? So so this, I think I've shown much earlier, the statement from Peter Bradshaw, that basically when people say they regret that we don't understand turbulence, is in his opinion what it means is we are just unable to integrate, numerically integrate the Navier-Stokes equations in our head, okay? We are not able to calculate this, process it, you know? So we just need an extremely large supercomputer. In those times, Cray was a very big supercomputer a company. Today we have many producing big supercomputers. So basically what he is implying is that the computing power is the limitation. This is the biggest disadvantage of the technique called direct numerical simulation. We just don't have supercomputing power in this world to actually calculate the flows that are of interest or flows that are have industrial relevance. That is the problem. So computing power limits the usage of DNS, and it's expensive. So we'll see like why it is expensive and why computing power required is so large. So then let's define what is direct numerical simulation, okay? So there are two words here, direct, numerical simulation. So the direct here implies that turbulence is not modeled, that I already told you in the beginning. No turbulence models are used when we do DNS, right? So that means no physical phenomena shall be modeled. Example, if you have turbulent combustion, a heat transfer, or if you can have hydrodynamic instabilities, thermal instabilities, you can have turbulent two-phase flows, whatever physical problem you have defined, it should be calculated using Navier-Stokes equations. It's a system of three equations: conservation of mass, momentum and energy, which is sufficient to solve any of your problem. You must rely only on them. You should not do anything else other than using these three equations, okay? So that's why the name direct came into existence there. Then the numerical simulation, it's not like numerically simulating any other equation. It has to be the Navier-Stokes equations. Okay, so and the numerical simulation of instantaneous, that is unsteady, three-dimensional Navier-Stokes equations. That means full Navier-Stokes equations has to be solved numerically without dropping the unsteady term, without dropping some direction. Sometimes you do like two-dimensional flows or one-dimensional flows. This is not allowed. That's because we already defined that turbulence is three-dimensional unsteady, right? And this also implies that DNS is applicable only for transition and turbulent flow problems. That's because for a laminar flow, there is nothing like an indirect method. Indirect method implies turbulence modeling, right? Suppose if you have a turbulent flow or a transitional flow, you can go ahead and use Navier-Stokes to solve this, or you can use some RANS models also to solve this. Whatever the accuracy is, but you have an option. But when you are solving for a laminar flow, there is no indirect method. There is no modeling idea there, and therefore DNS. I mean, if you cannot. I mean, you can call it, but it is recommended that DNS be used, the terminology for transition and turbulent flows. Okay, while you are solving full Navier-Stokes equations. And the third criteria is that all scales of turbulence, temporal and spatial, has to be captured or resolved. That is captured by your time step and grid. This is where the previous lecture will come in handy for you, where we discuss what is the smallest scale in a turbulent flow: velocity scale, length scale, time scale, right? The Kolmogorov microscales. So as long as you are capturing those scales in your flow, then this is your simulation will qualify to be called direct numerical simulation. Okay, so your grid, that is delta in x, y, z direction, must be smaller than or equal to Kolmogorov length scale. Okay, or an order or of the same order of magnitude also in some cases, and your time step delta t equal to the tau eta, the time step or the Kolmogorov time scale, and this is the Kolmogorov length scale, right? The length, the time scale. So that means you need to capture all the way from an integral scale to a Kolmogorov scale. And we have seen from Kolmogorov hypothesis what is the ratio between them. Suppose if this is your integral length scale L and this is your eta, we have seen the separation, right? So the L by eta from Kolmogorov hypothesis is 1 by Re raised to 3/4, right? Sorry? 1 by what is it? Eta by L, yeah, okay. Eta by L is 1 by Re 3/4. So we have seen the scale separation between the smallest and the largest. So one can go and estimate in a given problem how small L or how small the eta will be for a given Reynolds number, and your mesh size delta x, delta y, delta z has to be eta, right? So one can make a simple calculation. For example, if you take Reynolds number, let's take Re to be let's take a velocity of 1 meters per second, and length scale also 1 meter of a pipe flow or anything of that sort. And then let's say it's air, so it's roughly, let's say, 10 raised to minus 6. Then this is usually 1 million Reynolds number. So to compute a flow where Reynolds number is 1 million, what would this be? So L is now 1. What would this eta be now? Can you calculate and tell me? So what would this give me eta to be? The smallest mesh that you have to compute. If you have a calculator, you can It will be in few millimeters, micrometers. Sorry? 32. You got 32 micrometers. Okay. So you can see the size for a 1 meter, and this is the smallest mesh that you would need in this flow. And if it's 1 meter, that means this is the delta. So 1 divided by this. So you need to mesh like this. Let's say if you do an equidistant mesh, each mesh will have approximately this size, up to 1 meter in one direction, and in the other two direction. If the length of your pipe is very long, you will have many such grids. So you can see it's a lot of grid points are required basically. Okay. So now other questions that we can ask is, are these direct numerical simulations? For example, can we call steady state Navier-Stokes simulations as DNS? No, because turbulence is always unsteady, right? You cannot drop the unsteady term in the Navier-Stokes and simulate and say this is DNS. It's not. And two-dimensional Navier-Stokes simulations, that means you have dropped one of the term, and you know what happens when you drop one of the direction, not a term, direction. What does happen when you drop one direction in a turbulent flow calculation? Redistribution rate. Have you forgotten about it? Right? If you have all the three directions are important, right? Even though you may see that the mean flow is only acting in one or two directions, doesn't mean that you have to drop the other directions, because turbulence is redistributing also. You need to help the turbulent flow do that, right? So turbulence is always three-dimensional. All flows, in my opinion. There can be exceptions. As I said, this is this 2D turbulence is something, as I already discussed, is more or less hypothetical. So most practical flows or flows that we see are three-dimensional. And also instantaneous three-dimensional Navier-Stokes simulation of laminar flow. This I already told you. For laminar flow, there is no indirect method, right? So there is no indirect method here, and therefore in strict sense, we usually don't call it DNS when we solve laminar flows using full Navier-Stokes equation. Okay. And also, if your grid size, both temporal and spatial, okay, temporal means delta t, the time step here. Spatial is delta x, delta y, delta z. If that is significantly larger than Kolmogorov microscales, then obviously you are not resolving all the eddies, all the scales of turbulence. Again, you should not call it DNS. Right? So these are the pointers when we call it DNS, or at least if you are doing DNS, you must be aware of this, that you must make sure that you are resolving all the scales, use the full Navier-Stokes equation, okay, and to prove that it is DNS. Because this data will be used by others, especially those who are doing modeling, to validate, right? They are going to say if their model is good or bad, relying on your data. So you must do it correctly. So once you have the equation, then of course it's obviously at the end of the day it's a CFD technique. So there are many numerical recipes. There is no nothing like you have to use one particular technique. So all you have is this full Navier-Stokes equations, and you can discretize using whatever technique. This is not like I'm recommending a particular technique here. One can use pseudospectral solution where you have Fourier Chebyshev polynomials. Finite volume is popular, finite difference, finite element. Any method that you feel is good, you can go ahead to discretize. And people are familiar with, those who have some basic CFD knowledge are familiar with these three properties of numerical schemes that you choose. That is, scheme should be conservative, bounded, and transportive. Okay. For example, finite volume schemes, all the finite volume schemes are conservative by definition. Okay, we take conservative form of governing equations there to solve. So finite volume schemes are by default conservative, and the central differencing scheme is unique here, because I'm going to tell why I'm mentioning only that. This is actually not a bounded scheme. In the CFD, you would have learned in your CFD course that CD schemes introduce oscillations, numerical oscillations, and they are unbounded. So it is generally not recommended to use CD schemes. That is what you would have learned in the CFD course. And CD schemes are also not transportive. They do not reflect the flow of information, the directional dependency, whether it's a convection driven, diffusion driven, it doesn't recognize that. So for these two reasons, we generally say don't use CD scheme. But when we solve Eddy resolve techniques, direct numerical simulation, large Eddy simulation, and so on, it is recommended to use central differencing scheme in DNS, LES, and other Eddy resolve techniques. In RANS techniques, you may not use it. Okay. So why are we recommending CD scheme here, despite it is giving numerical oscillation? Is first thing is, as I said, DNS grids are so tiny that numerical error becomes negligible, right? Your mesh is going like in, you just saw like some 30 microns or so. The mesh is so small. So the error in a CFD calculation reduces with the mesh size. Smaller the mesh, lesser the error, irrespective of your numerical discretization scheme. So this does not mean that the oscillation is becoming zero, but the oscillation, we want this oscillation to be there, but minimal. That is the second point. DNS requires numerical perturbations, analogous to physical perturbations in nature. So it's very easy to start turbulence in laboratory or in nature because the background flow has perturbations, oscillations. It's not a clean environment in lab or in nature. There is always some perturbation which is aiding the turbulence to kickstart. But when you do a CFD calculation, the environment is so clean, right? You are giving an initial condition where everything is quiescent, everything is uniform. Then how do you bring this chaos or randomness inside, right? So of course the Navier-Stokes equations help, the nonlinear terms help, but you need to help the equation also. There is also a term which is the viscous term trying to get rid of these oscillations. So an unbounded scheme like CD scheme will be of use, and it is generally recommended to use it, okay, because it gives you small numerical perturbations. It is small because your mesh itself is very tiny, okay. And again, you can use any type of mesh. This is completely your free choice. Staggered grid, collocated grids, boundary fitted, body fitted grids, or overset grids, whatever, cell centered, node centered, all the techniques, whatever is your wish list. That is not a problem here. Only the mesh size is the important factor, not the methods and the schemes that you are using here. And this Poisson equation becomes critical when we do DNS, because most of the computing power goes in calculating the pressure field, and I'm talking about incompressible flows. So you need very strong iterative solvers or accelerators like this multigrid, or using this SIP or successive over relaxation, all these techniques. You need accelerators to make the flow converge, and this will be the most critical part in the computational perspective. What is the computing power required? The boundary conditions are easier here. You're only solving for 3 velocity components, 1 pressure, right? So pressure is set Neumann, velocity is its Dirichlet conditions, like you have no slip and kinematic boundary condition. You don't have to worry about boundary condition, is straightforward. And since the mesh size is very large, okay, typically goes into tens or hundreds of millions or even a billion. If the mesh size is so large, you would need lots of memory, right? Probably several hundred GBs or even a terabyte of memory is required. So with that kind of memory requirement, a single computer cannot do this, right? The memory on a single computer typically goes like maybe maximum 100 GB or so. You would need like terabytes of RAM memory. Then obviously you need to parallelize the code, your solution, and MPI is the default useful technique, message passing interface. MP can be done for small problems, because MPI is required if you are having a very large problem. Parallelization is straightforward, or not straightforward, I would say it's only viable technique is MPI for very large problems. Small problems which can fit in a one particular node with multi-core architecture, you can do MP parallelization also. Okay, this is the important point, the grid resolution. So what I already told you, you need to resolve all the scales of turbulence, temporal and spatial. So if I am looking into spatial grid here, let's call it delta. Okay, so this delta can be delta x, delta y, or delta z in the 3 direction, the spatial grid, and I'm looking into an order of magnitude. So I have 2 pointers here to make sure that the mesh is good. One is of course the Kolmogorov length scale, eta, right? So when you make a calculation, let's say you have chosen a mesh which is 100 by 100 by 100 grid points in 3 directions, then you can compute dissipation rate after the simulation is done. Using that, you can compute your Kolmogorov length scale in that simulation. Then you can compare your grid delta x, delta y, delta z with eta. If it is not good, then you refine. You make a better grid. Maybe you do 1000 grid points in each direction. You become a 1000 cube grid. Then you make a simulation. From the simulation data, you compute dissipation rate epsilon. Then you compute eta. And then again you look into the ratio of your grid delta by eta to see whether it is delta is smaller or equal to eta. So this is the direction you can go in when you do the calculation, and you can use the Kolmogorov hypothesis to make your first guess of the mesh, because you don't know what is that first simulation mesh that you would need, right? For that you have this ratio of the integral length scale to the Kolmogorov is coming from the theory. You can use it, and if you use that, this L by eta that we just discussed, scales like Re raised to 3/4 using the Kolmogorov hypothesis, right? So this is your Kolmogorov hypothesis here, using that. So L is, let's say, in one direction, x. What about y and z? So in each direction, if it is scaling like Re raised to 3/4, it becomes Re raised to 9/4. So n cube is the mesh in all the 3 directions. If you have a box, okay, let's say this is your numerical domain. So where this is your all the 3 direction, let's say nx, ny, and let's call this nz. So this n cube is nothing but your nx, ny, nz is your n cube here. The total number of grid points that you would need. Not the length, I'm not talking about the length here. N is the number of grid points along each direction. So n cube will go like this according to the Kolmogorov hypothesis. Very large. Okay. For the same problem, can you see what it is? The Reynolds number 1 million, what will be n cube? For, I mean, we just discussed, let's say 1 million Reynolds number, where u is 1 meters per second, L is 1 meter, air, take the air as the fluid. What is it coming? N cube. Example, Re equal to 10 raised to 6 will give, what will be the n cube? Even if you square it, it is 10 raised to 12, right? 10 raised to 17. You can see the mesh. 10 raised to 9 is billion, a billion degrees of freedom. Okay, so you can compute here how many trillion, not even billion, degrees of freedom is required, and whether you can do that kind of a mesh. No, I have not seen any DNS calculation where Reynolds number is 1 million. Even for a flow where 1 meters per second and 1 meter pipe, which is usually common, people would have seen, right? In that kind of a scenario, this kind of a flow, there is no supercomputer on earth which can handle 10 raised to 17 mesh points, degrees of freedom. So that is a limitation that we talked about in the beginning. No supercomputer on earth is available to do high Reynolds number turbulent flows. Okay, so Reynolds number is the limitation here. We can do only low Reynolds number turbulence using DNS. Okay. And some of the studies, like these are again literature, some note that the actual dissipation, it does not occur at the Kolmogorov length scale eta, but something like 15 eta. But these are literature. These are of course special flows. So in general, it's better to look at delta compared to Kolmogorov length scale eta. Okay, this is only a result of a particular problem where you see that at 15 eta is where the dissipation is occurring. So that means 15 eta mesh is fine. But in general, I would use always eta to be less than, or sorry, the delta to be less than eta, not eta, delta to be comparable to eta, same order of magnitude. Okay, that's what I would use. Slightly larger is also fine, but not greater than the order of magnitude. It's better to have the mesh size and Kolmogorov length scale same orders of magnitude. Equal is good. The other pointer that one can use is viscous length scale that we discussed, right? Your nu by u star, that is used to make your y plus and all these things, right? So you are using this to get your inner scaling coordinate system or coordinates. So you can also compare your mesh size with the viscous length scale nu by u star, provided you are working with wall turbulence. If you have jets, wakes, mixing layer like open flows, then better to compare with the Kolmogorov length scale. Only if you have a wall bounded flow, a boundary layer flow, or wherever wall turbulence is present, then you can use this viscous length scale nu by u star. I'm just showing here some example. So this is the plane co-ed flow that I've been talking about. Plane co-ed flow, turbulent plane co-ed flow. So here I'm looking into, on the left side, for this left side figure here I have what I'm looking into here is that the y-axis is representing max of delta x, delta y, delta z. This is some of the best practice guidelines I'm giving for DNS. So what is plotted here on the y-axis is I'm looking into the max of the size, okay, everywhere. So you look at, it's a 3D calculation, right? So you look at max of this delta x, delta y, delta z at every point and divide by the local Kolmogorov length scale at that particular point. Let's say you have 100 million mesh, then at each mesh point take the max of this. Of course, if you have equidistant grid in all three, then it is fine, but sometimes you stretch the mesh. So maybe delta x is larger than delta y and smaller than delta z, okay, and non-uniform mesh, then take the max of this, because you are preparing for the worst case scenario. Take the max of this, divide by eta, and then here this is the wall normal direction basically. So I'm just plotting here. So now you can see that it is not equal to eta. The mesh size here, the max of this, it is going like 3.5, 4 or something. So this is also acceptable. So that means this is, that means your delta here, so this is the delta by eta, right? Delta by eta is now of the same order of magnitude, right? So delta comparable, same order of magnitude, which is acceptable. Or there's another criteria called Grotzbach criterion here. This is also used. So where, as you see here, it is the cube root of this, right? So here delta is defined differently. Y-axis delta is essentially delta x, delta y, delta z cube root, okay, divided by pi eta. So this criteria is also popular to use, and when I plot that for the same problem, again this is the wall normal direction. This is y by h, of course this is in the y plus coordinate, same problem. So I can see now it is less than 1. So this is good, right? So now the criterion has to be less than 1. criterion value should be, whatever you are computing here should be less than 1, so which is good here. So it qualifies. If it's not, then you refine the mesh and redo the calculation again. That's what it is. So this is when you are comparing with Kolmogorov length scale. For the same case, you can also compare with viscous length scale, because this is a wall bounded turbulent flow, right? It's a plain turbulent coed flow. So here I am comparing a large table where I am comparing here our own data with some reference articles, and focus on these things. The last 3 columns, delta x plus, delta y plus, delta z plus. That means your mesh in viscous scaling, that is delta x by your viscous scale nu by u star. That is what is done here, right? So y plus is essentially your u star y by nu, right? So that y was the length, that is replaced with the delta x. So this has to be looked at every grid point. It's not like at one location you see and it is qualifying as DNS. It's a 3D volume. Everywhere it should qualify the criterion. So as you see, this is our data. There are reference data as well. Sometimes you see that the mesh can be much larger here. Usually it should be of the same order of magnitude, like this. So it is less than 10, right? So our delta x is now the same order of magnitude as viscous length scale. So it should not be 10 times larger. This is in the x direction, and this is in the delta y is actually the span wise, and this is the wall normal. So it's the other way. So let's call this y in our terminology, and this is z. Okay, so wall normal is, you see, it is much tinier, 0.41. So this is the y plus, the first grid is set at 0.41, right? I have told you to put y plus 1 at least, right, in RANS when you used low Reynolds number formulation. Here I'm using more, I'm having more grids there because I need to compute the gradients also there for the wall shear stress, right? So I'm having more points so that my wall shear stress data is better. I need to compute du dy on the first grid point. So generally we put many grids inside y plus 1 in DNS, maybe 5 grids, 10 grids, as much as you can afford. And the largest grid along y is 1.71 of the viscous length scale at the center of the channel. So it is very little stretching, slow stretching from 0.41 to 1.71 at the center of the channel. Okay, all right. So